So what I just passed around are a few of the little survey things. These are not for now, they're for later. I will come collect all of these later, or you can come say hi and hand it to me once the session's over. If you have to skip out or something, if you need to leave for an exam or you need to leave for whatever reason, you can fill it out in advance. Just leave it on the table, no big deal. I'll come pick it up later. These are just so we can keep bringing awesome stuff for you, and you can tell me how to improve in the future. So there's that. So just so I kind of know, who's Professor Sukora's class? Durrani? Udine? Okay, all right, cool. So we got a good mix today. So this session, just as a brief overview for you guys, it's designed to be a very general overview of the course, kind of from the beginning, more up to where we are now with that two-sample hypothesis testing, confidence intervals, that type of stuff, inferential statistics, we call it. I'm not going to spend too much time doing the basic calculation stuff. What I have done, though, is given some example problems in my packet online. And then when I post the solution guide, you can see all of the work worked out for them. But things like calculating standard deviation, calculating variance, on the way to that, you can easily find a Khan Academy video online. I don't want to waste your time doing that here. So if you have specific questions about that, what we can do is at the end, I'll leave about 10 minutes for you to come and ask questions or raise your hand and ask questions. And we'll also have about a 5-minute break to get some water in the middle of the session. And you can feel free to ask me questions then as well. Okay? So another notification, this session is being live streamed. So if you decide to run around in a chicken costume, it will be preserved online forever. Please don't do that. Basically, if you have a question, that's cool. We're going to try to keep it to a minimum and not ask any questions that aren't absolutely necessary. That way we can just keep things moving. If you have a question you think, oh, this is just a little detail thing, just feel free to come and ask me during the break at the end of the session, and we'll straighten it out then. Any questions about live streaming or anything? No? Okay, so the live stream is live now, but it will be recorded, and then the recording will be online for you guys later. So if you're like, wow, he went really fast, I didn't catch that, you can go online and watch it later at half speed. You can go online and say, Justin talks way too slow, and watch it at double speed. It's up to you guys. So thanks for sticking with me. Thanks for being here at 8 o'clock in the morning. I know it's a good start to finals week. So that being said, on the board up there, I have it written out, but at the UCF Study Union WordPress site, you'll find my packet on the Statistics and Mathematics page. Was everybody able to find that, print it out, see it online somewhere? That will be very helpful. So even if you can pull it up on your phone or your computer, or you have it printed out, that's great. That's what we're going to be following along with right here. So this is just that packet. We're going to go through it together, and we're going to chug through as much of it as possible. So we are going to start right on page 1, because that's a very logical place to begin. And we'll do a brief overview of our distributions if we think way back to the beginning of the course. So I think we all remember seeing graphs that look something like this, where we have symmetrical distribution, which you guys are very familiar with at this point. Symmetrical curve, if we remember properties, we have the same amount of area on the left side as we do on the right side. The mean, median, mode are all smack in the middle of the curve. Very even, very nice. This is what do we think about when we look at this? We think about z distribution, z curve, which we'll get to later. And then in the next graph, we see a positively skewed distribution. When I think positive skew, I'm typically thinking of everything in terms of like a class. So say we have a stats class, everybody takes an exam. The people, let's say some people scored really high compared to the rest, that's going to skew the distribution to the right, producing a positive skew, which, as we see, pulls the mean up. Meanwhile, the median is much less susceptible to change. That's a property here. So with the median not changing very much, the average or the mean gets yanked up by those high scores, skewing the distribution to the right. Now, in the case of the negative skew, we just had a bunch of people do not so well on an exam, which pulled the average down. But again, with the median not being very susceptible to change, it kind of stayed put closer to the top of the mound. So if you ever get one of those questions where they're like, what happens to the shape of the curve if this were to occur? And it's an example, something like a test or something. You can just basically think in your head, which way is the mean going to go? The median's more likely to just stay put. And you can just draw a quick curve and throw some lines on there. So that's one way to go about those types of questions. Quick terminology review. We have X bar, sample mean, mu, population mean. These will mainly come into play when we start looking at formulas. But for now, we're just going to remember which goes with which, and we'll be good. Most of the Greek letters will be with population, and everything with a bar is typically referring to a sample. So if we keep chugging along, quick review of how to calculate mean. Excuse me, guys. Sorry, my throat. So let's say we have a list of different trucks. They all have a different mass. They give us these numbers. How do we calculate the mean? Well, if we remember back to the beginning of the course or earlier in life when we learned this, we're going to add up all the numbers, divide by how many numbers we have, and we should get something close to 3126. And notice that this number is not too extreme, meaning it's not higher than any of the numbers really here. It's not lower than any of the numbers here either. It should make sense with the distribution of the numbers that we have. The main takeaway from this is that conceptually, if you were to get a question that asks, hey, what's the mean of this sample, or does the mean of a sample have to be a data point in your set? That question we can answer using this number. If you guys can check me on this, and you'll see it on the solutions manual, but this number is clearly not one of the truck weights that we measured when we weighed all these trucks. So the mean, our calculated mean here, does not have to be a possible point in our data set. So that's important. Just because the average truck mass is 3,100 kilograms does not mean that one of the trucks we measured had to be 3,100 kilograms. So that's the main takeaway from this. I don't want to spend too much more time on that. So now if we go over and we flip to page 3. So this stuff is very helpful. Terminology reminder: population variance sigma squared, population standard deviation sigma. So these guys, again, come into play later when we start writing curves and dealing with formulas. So first big rule that deals with some distributions and has a bit of math involved, we have Chebyshev's rule. So Chebyshev's rule, if we remember from earlier, is going to apply to any data set. Any data set meaning they tell me it's skewed, they tell me it's not normal, or if they don't tell me the shape of the curve at all. So that's very important. If I don't know the shape of the curve, I can't use empirical rule. I have to use Chebyshev's rule. And Chebyshev's rule mathematically is going to be 1 minus 1 over k squared, where k has to be greater than 1. And that value will represent the percent of measurements that lie within k number of standard deviations of the mean. So k is just our number of standard deviations away from the mean on either side. Now, the key word here is that this is going to be at least whatever percentage of 1 minus 1 over k squared measurements. So the reason that's going to become important is when we start interpreting the other areas of the curve, and we'll see that when we do our example problem. And then the reminder of empirical rule, which we can only use if we have a mound-shaped symmetrical normal curve. All of those are trigger words for the same thing. They have to tell us that the shape of the distribution falls in that category. This follows some pretty steadfast numbers. Your book might vary very slightly from these, but it's pretty much standard across the board. 68% of our observations will be within 1 standard deviation of the mean, 95% within 2, 99.7 or so within 3. And that's just referring to our curve. If we have a curve and there's z of 0 within 1 plus or minus 1, that's our 68%. And then if we were to go to 2, excuse my crude drawing, if we were at 2, that'd be about 95%, so on and so forth. And what we can do is we can break that down and do some quick subtraction to kind of get really good guesstimates on percentages of observations between 1 and 2 standard deviations, 1 and 3 standard deviations, and that sort of thing. Something that's really, really important, which hopefully everyone has mastered by now, generating a z-score. So if we're generating a z-score, we have an observed value, we have our mean, we have the standard deviation of whatever we're working with. Say it was the truck example. Say I had a truck that I observed to be 2,122 kilograms, and the average truck weight we said is about 3,100 kilograms. So just from the numerator alone, I know that if I'm subtracting a smaller number minus a larger number, I'm going to have a negative z-score. That negative z-score is just going to indicate to me that this observation is below the mean. 1, because we know the observation is below the mean of 3,100. 2, if it's negative, we're going to be on the left side of the curve, right? Negative z is on the left, positive z is on the right. So if we do this quick math, let's say, I'm just making up numbers here, if the standard deviation in truck mass was 122 kilograms, then that would be our standard deviation on the bottom. So that's kind of where everything got plugged into. And if I do random calculator button pushing, we'll get a z-score of -8.01, blah, 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 blah. So this is very, very, very much below the mean. Now again, this is just made up numbers, but that's basically how it works with plugging things into the formula. So if you struggle with this at all during the course, come talk to me during the break and we'll do a quick example together. So on to application of these rules. So let's say we work at a candy factory, because that sounds like a really, really good job. And we record the number of pieces of chocolate that are produced at this factory every day of the year. The company that owns the factory wishes to study the changes of production in order to understand how they may optimize candy production to boost profits, because who doesn't want to make more money off of candy? For the company, chocolate tastes good, but money is better, obviously. Now, one objective of the company's study is to see what percentage of days less than 3,000 chocolates were produced. So you can kind of follow me as I underline through this, but I'm looking to see what are they even asking about, right? All this so far has been not nonsense, but not really relevant to what they're actually wanting. So they say over the course of 1 year, average number of chocolates produced per day is calculated to be 4,500, standard deviation of 500 chocolates. So now they ask, what can you say about the percentage of days where there were between 3,500 and 5,500 chocolates produced by the factory? Well, interesting question to answer. So if they didn't tell me anything about the shape of the distribution, which I don't think they did, and in the question they say, assume you know nothing about the shape of the frequency distribution, does anyone have an idea about which rule we should be applying? Chebyshev's, yeah, so we're going to apply Chebyshev's rule because we don't know the shape of the curve. So if we're applying Chebyshev's rule, what we're going to do is we're going to make a z-score for this observed value, and then we'll go from there. So if we remember, z-score equals x minus, I'm just going to use everything in terms of sample here, observed value minus sample mean over sample standard deviation. And that, for the first one, will be 3,500 minus the average of 4,500 over the standard deviation of 500. The second value will be 5,500 minus the 4,500 over the 500. So this one will give me a z-score of -2. This one will be a z-score of +2. And so now this value, if we remember Chebyshev's rule, so k is just referring to our number of standard deviations from the mean. We know that these observed chocolate production values are regarding distance from the mean. So this is our k. So we're going to have at least 1 minus 1 over 2 squared. We're just going to plug it in. So that will be 1 minus 1/4, which will be 3/4. So all we can say now is at least 3/4 of the days of the year they produced between the 3,500 and 5,500 chocolates. So we just say at least 75% of the days they produce between blah, 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 and blah, 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 blah. And we just kind of fill it in from there. So this is really what they're looking for. So in part B, they ask us, what can we say about percentage of days when less than 3,000 chocolates were produced? And still, we don't know anything about the shape of the curve. So if we want to know less than 3,000 chocolates, first step, let's just make it a z-score. Let's get everything in terms of z, and then we'll just kind of go from there. So if we have 3,000 minus the mean of 4,500, which has not changed, over the standard deviation for that is 500, which will give us a z of -3. Great info. So now if I were to kind of pictorially represent this with a really kind of crude drawing, if we have -3 and +3, I'm drawing this as a partially kind of symmetrical curve, but we don't really know the shape. This is just for simplicity. So if our z-score is here at -3, this is where that observed value of 3,000 is really sitting on a curve, then they're really asking less than 3,000, so they kind of want something in this area. They want a tail region of the curve. Whether it's symmetrical or not, we don't know, but it's going to be something to the left of -3. So what can we do? Well, we can kind of work with Chebyshev's rule and make some guesstimates here. So if we know we have at least 1 minus 1 over k squared % of our observations within k standard deviations, if we plug 3 in, we'll know that we have at least 1 minus 1 over 9, 3 squared is 9, 1 minus 1/9, or 8/9 of our observations in this zone here, from -3 to +3, because we're that many standard deviations from the mean. So if we know we have at least 8/9 here, then in either of my tails, my hypothesized tails here, we can have at most 1/9 here or here. Whether they asked greater than 3 standard deviations or less than 3, that answer would be the same. So at most 1/9 of the days out of this year, they made less than 3,000 chocolates with this factory. Okay? So if you have questions on this and the wording, which is usually the most confusing part for people, just let me know later and we can have a chat about it. So now when we kind of switch gears here, they ask us, what is your answer? We just kind of rework the problems if we know that we have a mound-shaped distribution. So what changes if we have a mound-shaped distribution? What can we do? Yeah, empirical rule, right? So empirical rule is for mound-shaped curves. So if we're working with empirical rule, well, this becomes, I wouldn't say more straightforward, but if we know the numbers, it's a bit straightforward. So in part A, we know we had z-scores of -2 and +2. That's not going to change. So if I were to just draw a quick normal curve here, oh, we have a z at -2, z at +2. What's the percent of observations within 2 standard deviations of the mean? By empirical rule, will be approximately 95%. And that's just you having your numbers written down on your sheet or having them memorized, whatever you need to do. You know it's approximately 95% of the days they produced within 2 standard deviations of the mean, or between 3,500 and 5,500 chocolates per day, about 95% of the days of the year, if we know we have a normal mound-shaped curve. So in part D, they say, what would your answer be to part B? Well, part B, they asked, less than -3 standard deviations. So if here's -3, they want that tiny little tail region. Well, we know by empirical rule, within 3 standard deviations was approximately 99.7% of our observations. So we know a few things. We know we have 99.7 from -3 to +3. And we know the whole curve adds up to like 100%, right? Because we have all the probability, all the area under the curve, totals to 100. So if we yank out 99.7% from the -3 to +3 region, that means between these tails, we're going to have 100 minus 99.7, or about 0.3% left over. Now, that percentage, due to the fact that we have a mound-shaped curve, will be split evenly amongst each tail. So we'll have 0.15% there and 0.15% there. So what's the area here? Approximately 0.15%. So approximately 0.15% of the days, they produce less than 3,000 chocolates. So then they could ask you some sort of a qualitative question where they say, based on this knowledge, would it be a rare event or a common event for this factory to produce less than 3,000 chocolates in a given day? And well, what we would say to that is if they only produced less than 3,000 chocolates on a given day 0.15% of the time, that's practically never. If we were to take 0.15% of a year, not a whole lot of days. So we would say it's a very rare event. So that's just an application of a simple question like this, or what I would call for the class a relatively simple question, and then have you make a general conclusion about that. Typically with a question like that, you wouldn't be asked anything crazy or anything that's borderline. It should be pretty obvious whether they want you to know it's a rare event or a common event. Either it'll be something like that 0.15% of the time, or it'll be 99% of the time. So hopefully it shouldn't involve a lot of thinking if you do see a question like that. The important thing is knowing the wording and knowing the rules. That way you can just apply everything quickly and be done with the problem. So in this last part here, what can you say about the percentage of days that the factory produced between 3,500 and 6,000 chocolates? Well, that is a lot of chocolates for the first part. If we were to make z-scores, we know for the 3,500 number, that gave us a z of -2. For the 6,000 number, I'll spare you the math, and we'll just say that gives me a z of 3. So by empirical rule, we would draw that curve out. We know from -2 to 2, we have the 95%, or approximately 95%, and then -3 to 3. Sorry for the really gross drawing, 99.7%. And what we can do here is some subtraction and division and get this little area here and tack it on. That way we have the 2 to 3 transition in the standard deviations, which will give us a grand total of 97.35%. Now again, all of these are approximately, so approximately 97.35%. We don't say exactly, because it could vary a little bit. There is some wiggle room here. So if you have a question about this last one, I just suggest you read over the solution manual or ask me during the break, and you will be golden on that. Any questions so far? Just want to make sure we're on track. Okay, cool. We are at 8:20. Doing good, guys. Let's go to page. Let's shoot for page 5. Why not? So if we're on page 5, we're getting into the most loved section of the course, probability. Now, I know a lot of you probably struggle a lot with this section, as most students do. The key here is to not be scared of it. Know that you can do it. It's not impossible. If this was your weakest spot in the course, I would recommend studying this the most, obviously. You want to be strong here. So I'm going to zoom in a little bit so we have a better view. Cool, so we get 5 problems for homework. Yeah, right. So at the next class, 2 of the 5 problems are going to be selected, and the professor is going to collect them for grading. And you being a, I wouldn't say mediocre, but they're not the best student, you've completed 3 of the problems. So they want to know what's the sample space of the experiment if we were to collect 2 problems at random. So we can kind of label the problems A, B, C, D, and E for problems 1, 2, 3, 4, 5. And one possible selection, they're giving us an example, would be you select problems A and B. That would be an example of a point. So blah, 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 blah. If these 2 problems are selected, did problems A, B, and C, you will be able to turn in both problems. So there are 9 other possible selections to consider. So if they're telling us we have problems A, B, C, D, and E, the 5 problems that they assigned. Now, they told us one example of a point would be A, B. So now we basically just need to list off what are the other options, what things in our sample space here could we have if we're just picking 2 problems. The professor could select AC, AD, AE, we could get BC, we could have BD, BE, we could have CD, we could have CE, and last one, DE. And they told us there were 10 options, so we can do check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they're all different. So we should be good to go. So one thing we don't want to make the mistake of here is saying AB and BA. BA would be the same as AB if we were to just look at what's in the sample space. So there's no need to double all of these and say, oh, there are 20 possible combos. Just these 10. So in part B, they ask, are the outcomes in the sample space equally likely? Well, if you just did 2 of the problems, that doesn't even matter. The professor's just picking them. So if the professor's just picking problems, you don't know which ones he's going to pick. To you, it's pretty much random. You can pick A and D, you can pick B and E, you don't really know. So if each of these independent events, the problems being picked, have the same probability of outcome, well then, yeah, each sample point should have pretty much the same probability. It's just as likely for the professor to select problems A and D as it is for him to select B and D, or B and E, or C and D. So we will say yes for part B. Each of them will have the same probability. Now, C is asking us, what's the probability that you'll be able to turn in both of the problems selected? So if we read back, which problems were selected? You did problems A, B, and C. So they're asking us, what's the probability that you'll be able to turn in both of the problems selected? Well, if we did A, B, and C, this would be good for us. This would be good for us. This would be very not good for us. A, B, C, B and C would be okay for us, and these would all be very bad for us. So these three options, sorry, I'll move down for you guys. These three options, A, B, A, C, B, C, contain the problems that we completed. So we have, they ask us, what's the probability we'll be able to turn in the problems that are selected? Well, we have 3 out of the 10 options fulfilled based on the problems that we completed. So we'll have a 3/10 or a 0.3 probability of being A-OK on this homework. So now you know when you take your odds submitting 3 out of 5 or whatever you do on your homework, if they're picking randomly, that's what we're working with. So in part D, they ask, does the probability we'll be able to turn in both problems change if you've completed the last 3 problems instead of the first 3 problems? Well, we just said every single event or every problem is equal likelihood of being picked. So conceptually, I'm kind of thinking, I don't see why it would make a difference, but we can kind of look and just do a quick test. So we have problems A, B, C, D, and E. Let's say we did the back 3. Let's say we did C, D, and E. Well, which problem sets would we be able to turn in? Well, D and E would be okay for us. C and E would be okay. C and D, this wouldn't, this wouldn't, this wouldn't, all of those wouldn't. So again, we have 3 out of 10 options. It's not going to make a difference if we were to do the back 3 versus the front 3. As long as they're all being randomly selected, no one really cares. Now, in part E, they're going to say, what happens probability if you can turn in both problems selected if you had completed 4 of the problems rather than just 3? So let's do another quick guesstimate. So let's say we did 4 problems. Let's say we did A, B, C, D. Yeah. 4 of the problems. So A, B, C, D. So this is now our set of completed problems. So A, B, C, D. So we have A, B, A, C, A, D. This is now fine for us. That's still not okay. B, C is okay. B, D is okay. B, E is not okay. C, D is yes. C, E, no. D, E, no. So we have 1, 2, 3, 4, 5, 6. 6 out of 10 are now good. So your odds of being okay on this homework are doubled by just completing 1 more problem. That's the concept they're going for here. We completed 1 more problem. We did problem D. And now instead of a 0.3 chance of being okay on this homework assignment, we're at 0.6. So the probability doubled. That's all they're going for on that. So a problem like this where they're kind of giving you this starting point, it's pretty relevant in that we all do homework every day. It might not be this relevant. It could be something very weird. It could be, you know, diameters of screwdrivers and weird things that are just nonsense to us. But we kind of have to be able to deconstruct it, determine a sample space, see how many things apply based on what they've asked for, and go from there. Any questions on this problem real quick? No? Okie dokie. So let's talk about, I think we're looking at mortgages now. So this will be applicable, I guess, in a few years if anyone ever plans to buy a house. So bank offers a couple different types of mortgage loans for residential properties. They're classified into 3 categories: single-family condominiums and multifamily dwellings. Each loan made in 2010, classified by type of mortgage, type of property, gave us this table. So they want us to consider a chance experiment or selecting where we're selecting one of these 3,750 loans at random. Well, that's nice. They told us there were in total 3,750 loans. So great tidbit of information. Now, starting with part A, what's the probability that the selected loan will be for an adjustable rate mortgage? Well, here's the adjustable rate mortgages. If we look that way, the total of adjustable rate was 2625. So for part A, we have 2625 selected adjustable rate mortgages out of all of the mortgages, 3,750. Now, if you really want to, or if the problem answer choices are all as decimals, then we would just divide and give the decimal. That'll be our probability as a decimal. For the sake of keeping everything accurate, I'm just going to leave it all in fractions. You guys know if you were to do top divided by bottom, that would be your decimal, that would be your probability, if that's what the problem's asking for. Is anyone not taking a multiple choice exam? I know most professors in here give multiple choice. So multiple choice, just go with whatever they give you. If they give you only decimals as answers, you know what you need to do, convert it to a decimal. If they're all fractions, it's going to be a fraction. If they're all reduced fractions, then you need to reduce your fraction. So you just kind of go from there and feel out what they're asking for. I think most of the time, though, this would be more than adequate. Should be fine. In part B, probability that the selected loan will be for a multifamily property. Well, multifamily properties, this column going down, we had 710 of them. out of a total of everyone, 3,750 mortgages. So that would be our Part B probability. Part C, probability that the selected loan will not, keyword not, be for a single family property. Well, single family was 1875, so there are a couple of ways to write this. If we're looking at Part C, not single family, we can write this a few ways. We can do the total, 3,750 minus 1875 over 3,750, or you could do 1165 plus 710 over 3,750. Those should give us an equivalent answer, as long as this math works out. In Part D, what's the probability that the selected loan will be for a single family property or a condo? So or, if we think back, or statements, we have things like and statements, and we have or statements. So if we say this and this, I'm thinking of an intersection. Two events, they both have to occur. With an or statement, I'm thinking of a union. It could be event A or it could be event B. Okay, these are very, very general explanations at this point. So in Part D, they asked family property, so I'm going to just write this out, single family, or, meaning union statement, or condo. So if we remember, when we're taking the union of these independent events, we will add up their independent probabilities and then subtract the intersection. In this case, we don't really have an intersection unless we can find one, so we'll just see what we can get. So if we have single family in union with condo, so the single family, 1875, and the condos being 1165, they don't seem to intersect anywhere, so out of the total, we should be left with that. I believe this comes out to 3,040 over everyone, 3,750. So you guys will see that in the solutions as well. In Part E, what's the probability that the selected loan will be for a multifamily property or an adjustable rate loan? This is where things get more fun. So we have a multifamily property, which is this column going down, or an adjustable rate loan, which is this row going that way. So the same story here with this union thing going on, this or statement. Multifamily property, there were 710 of those. Adjustable rate loan, there were 2625 of those. Well, we're going to have a little issue here if we just add these and then divide by everyone. Now, why would we have an issue? Well, if we have adjustable rate loans going this way, boop, 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 and we have multifamily going down this way, do, 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 so we have an arrow that way, all the way across. So this 2625 that we used, this 710, they are both counting this 337 value of multifamily and adjustable rate loans. So both of these numbers include this. If we were to just add this number to this number, we're going to double count this 337, which is why we have to subtract it so that we don't double count this. So once we do all this math, we'll just, math, and I think it comes out to like 2998, something like that, over 3750. So in more general terms, if we were to write this out, if I was asking for the probability of A union B, the technical way that I can write this is probability of A plus probability of B minus the probability of A intersect B, which is exactly what we just wrote. We had the probability of event A, the multifamily property, and event B, the adjustable rate loan, minus the intersection of multifamily and adjustable rate loan. So this problem here is going to follow this formula exactly. And I know you guys talked about this in class because I've seen all you guys come to me with problems, and we did stuff like this before. So make sure that you have this somewhere, along with conditional probability, which we'll talk with right about now. Let's go to the next page, page 6. So I'm going to let everyone kind of take a second to read while I drink for a minute, and we'll get our bearings. All right, cool. So this one's a fun one. We have a cable TV company. 80% of the customers have TV, 42% have internet, 32% have telephone, blah, 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 numbers all the way down. And then they want us to consider some chance experiment that consists of selecting one of the cable company customers at random, find and interpret the following probabilities. So they tell us these percentages, and then they say, oh, we're going to pick people randomly. What's the probability that this happens? Which we can do, A, B, C, and D, if we use the raw numbers. Personally, I think it'll be a little bit more confusing if we do it that way. What I would like to do in this case is kind of just write everything out and give you guys an example of how we might fill out a diagram such as the one that's drawn, even though it looks kind of awkward and weird. We'll see how everything kind of fits together with the puzzle here. So each of these 3 big circles that you can kind of see intersecting here, let's call this one TV customers, this one will be internet, and this one will be phone. So what I like to do is start at the middle and work my way out. So the middle is going to be corresponding to all 3 of them, right? All TV, internet, and phone, they're all overlapping to make this section in the middle. 15% of the customers subscribe to all 3 services. So I'm going to do everything. I'm just going to convert the percentage to, let's say, out of 100. So 15% for us will be 15 people out of 100 that have all 3 services. So I'm just going to use raw numbers here. So we have 15 there. Then what do we want to do next? 23% have internet and phone. Well, internet and phone is going to be this intersection here, and they said 23. So 23, but we can't double count 15, so 23 minus 15 should give us 8 being left here. So 8 of them have only internet and phone, but 23 have internet and phone total because these 15 happen to have TV also, if that makes sense. This will start to fall into place as we keep going. 21% subscribe to cable TV and phone. So TV and phone, 21 minus the 15 that are already here, leaves us 6. 25% to cable TV and internet. TV and internet, we have 25 in this section, minus 15 leaves 10. And then we get into the bigger numbers. 32% subscribe to its telephone. So 32 are in this whole circle altogether. So if we do this plus this plus this, take it away from 32, we're left with only 3 people. So if they were asked, what's the probability that the selected consumer only has phone service from this company, we would say 0.03, because 3 out of 100 people would have only phone service. And we can just keep going with this and fill in the rest of the boxes. 42% subscribe to internet. So if we do 42 minus each of these 3 that are also in this circle, we're left with 9. 80% have TV. This must have been a while ago when TV was like way more popular. We're left with 49 here. So now we can kind of start thinking about answering these questions. So if they said, what's the probability that I only have cable TV? Well, like we said before, that would be the people that are not touching any of the other circles, these 49 people. So we would say this guy right here equals 0.49. Now we get into the fun statements. Probability of internet, random line here, cable TV. What's the random line here is the question. I don't remember what we did in probability. Well, that little line is what we call setting a condition. So we have probability of internet given that cable TV is also on this consumer's bill, essentially. So the consumer needs to have both internet and cable TV, but we need to have assumed that he already had the cable TV, if that kind of makes any sense. So the way we can write these statements out, we're going to write a general form here. We have probability of event A given event B. This will expand out to probability of A intersect probability B. Sorry, probability of event A intersect B over probability of just event B. Now, conceptual note here. This statement here, probability of A given B, if I were to flip it and say probability of event B given event A, would these be the same in terms of the value of the probabilities? Well, there's only one scenario where that would be true. The scenario where these statements would be equivalent would be if event A and B both had the same likelihood of occurrence, or the same probability. Now, the reason they're typically different is because the top will not change. A intersect B is the same as B intersect A. That doesn't really matter how we write it. Now, the denominator, probability of event B is on this side because the second event goes below. Probability of event A is here. So unless these have the same value, these statements are not equivalent. So this might be in your book, it might not be, but this is kind of a conceptual statement on the fact that if we were to flip that statement, it's typically not the same value unless A and B were the same to begin with. So, on that note with our problem here, probability of internet given cable TV, well, if we were to expand this out, we have probability of internet intersecting cable TV divided by probability of just cable TV. So this was like our event A, this was like our event B. So internet intersect cable TV. Well, yeah, we can do that. So who has internet and TV? Well, a lot of people have internet and TV. We have 25 people. We have these 10, which have just TV and internet. We have these 15, which have TV and internet, and they also happen to have phone, but that's not really going to matter for us. So we have 25. So I'll just write this as a decimal, 0.25 for that probability, divided by probability of just cable TV. And we can look here and add all these up, or we can just know 80% or 0.8 have cable TV. So when we do this math here, I'm like getting really messy here, but this should come out to around 3125-ish. So around 31% of people have internet given that they have cable TV. So it sounds like an odd statement, but this is mathematically how that's going to work out. Now you could be asked conditional statements regarding any of the services. You know, you can be flipping statements. It doesn't really matter. Totally up to your professor, and you might not even be asked a question like this at all, but it's a pretty good tool to have under your belt. I'm going to let you guys work out part C with the review packet online that will have the answers. And we'll do a quick look at part D. Part T, internet and cable TV only. So that's the key word here. Only. So if we have internet and cable TV, what are we going to have to do? We're going to have to yank out a section of this to make sure we're not double counting. Now, Justin, what do you mean by that? Well, if we have internet and cable TV, that's these guys. Internet and cable TV. And we kind of indirectly did this in the last problem that we did. So internet and cable TV, well, 25 people, that 10 plus 15, 25 or 0.25, that's the probability of just having TV and internet. But they said only internet and cable, which means we need to remove these 15 that also have phone, because they will not fall into this correct statement. So 25 minus the 0.15 will leave us with the 10 in the other box. So that's our probability for that statement, internet and cable TV only. So try to be careful when they set conditions like that, that you're not either including a number that shouldn't be there or something else. Now, you might find this more confusing than dealing with these numbers. That's okay. You might find this really confusing, and this is easier to break things down at the end of the day. That's your preference. The only time it would not be your preference is if you were given a diagram that's blank like this, and you had to fill it out, which I don't know if that would happen, but it could. I'm sorry about my throat, guys. I'm like getting over being sick. What a Monday. So if we're looking at combinations next, if we remember our formula combinations, I think your book writes it something like this. Some books write it something like this. Whatever works for you will work for you. Essentially, we have big N, meaning this is the bigger number, little n meaning the smaller number of number of items in our subsets that we'd like to create. Now, when do we use combinations? Some of you might have also heard of permutations. I don't know if you talked about them in class or not, but we'll do a quick little chat. So our combinations are when we want to make some number of unordered items out of a larger group. So say I have a group of 20 students. How many different groups of unordered groups of 3 can I make? So if that were the case, then we would use 3 for our little n, 20 for our big N, and then we would follow this formula. Now, oh, Justin, what's the formula? Well, that's something you're going to want to have on your sheet. If we have this guy, then our formula will look something like this. if my pencil stops breaking. So this, whether or not it looks scary to you, we'll just plug in these random numbers. So let's say we had our group of 20 students. That's our big N. Little n, groups of 3. 3 factorial. 20 minus 3 is 17. We just did big N minus little n. Factorial. Blah, 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 blah. Do some math. This number, you can try it on your own. I'm going to try to do it by hand. Well, 20, 19, 18 over 6. So it should come out to this being the equivalent statement. You guys can math that out. But if we're sticking with the actual problem they give us, we're working with Jeannie here. Jeannie has 7 errands that she needs to complete, but only has time to do 3 of them because there are only so many hours in the day. So how many possible ways can Jeannie select the 3 errands that she will complete? So we have 2 numbers. 7 things to do, but we can only do 3. The bigger number is our bigger N. That's pretty much always how this is going to work. So if we're writing this out, we have big N on top. Little n, 7 minus 3 factorial, big N minus little n. So that'll be 7 factorial over 3 factorial, 4 factorial. Now, you can use your calculator to accomplish this task. That is fine. Or if you are super hardcore, you can write it out. Because if we remember, factorials are really just doing this. If we were to expand it, and I'll just leave the 1 out of the picture, and then the 4 would expand out to that. Now, this 4, 3, 2 will cancel with that 4, 3, 2. This 3 times 2 is 6, which cancels there. So this statement is really just 7 times 5, which we know is 35. So you can do it with your calculator. Some of these you can do it by hand just like that and be done with it. You can also use it as a second way of checking yourself. Totally up to you. On the calculator, I'll just show you real quick. For on the calculator, if you're using like a TI-84 or TI-83, they work very similarly. So if you want just the factorial button, there's your factorial button. You would just type a number and then hit that button and it'll do factorial. Of course, the last number I had in here was probably crazy big, and that way it won't take it. But if we were to do 5 factorial, and I scrolled over to probability on the right side, and then down to option 4, 5 factorial comes out to 120. It's doing 5 times 4 times 3 times 2 for you, and then just spits out the number. So you can do that. There are also functions in your calculator if you're using one of these, where if you go over to probability, you have NPR, NCR, PR for permutations, CR for combinations. And with those, you can plug in like the big N, hit that button, little n, or it works the other way. I can't remember which way. You can try it. One of the way it'll give you an error, and the other way it'll actually do it. Yeah, well, let's do it. Why not? So we used 7 and 3 last time. One of these ways is going to work. I don't do this very often, so we'll see. And that's it. So we gave it big N, NCR, little n, and it spits out the number, 35, just like that. So you can do that. That's one option. Yeah, make your life easier. Why not? It'll work for bigger numbers too, so I don't think it'll give you too much of a problem, but I would know how to write it out just in case something gets weird. Or if your calculator dies and you have to go to a scientific calculator that can't do it, something like that. On the note of calculators, if you did not know, you can go to the library and you can check out a graphing calculator, which I think they pretty much just use this model, TI-84 or an equivalent, for free for 24 hours. So if exam time rolls around and you're like, oh man, this would be so much easier with a graphing calculator because wow, this tiny little 4-function calculator is really hard to use. Go to the library, you just show your student ID, check out a calculator, use it for your exam, and then you're good. So you don't have to pay for it or anything like that. So in case you didn't know that existed, that exists. Use the library, it's a good resource. So that's that for combinations. Most problems will look something similar to this in that there's a larger number, there's a smaller number, and the key thing is that we're selecting just how many can we do out of this group, not how many ordered things out of this group can we do. If your course talked about permutations, you can do a quick problem with those as well. You would simply see a word such as like ordered subsets of k items or whatever it is, and we can go from there. So now, we're on to some more fun stuff, into what I would call more of the meat of the course once we're past probability. So we are on time. Right on track. Awesome. So if we're talking about p-hat, what are we thinking of? Well, personally, when I think p-hat, I like to think of surveys. So p-hat meaning sample proportion, right? This is written out for us. proportion out of a sample, sample proportion. You can kind of toss the words around in your brain a little bit. I like to think of if I just walked into Walmart and asked people a random question and record responses. Let's say I ask 100 people, is your favorite pie apple pie? And 80 of them out of the 100 people I asked said, yeah, apple pie is my favorite pie. If I were to say, what's the proportion of the sample that favors apple pies over all other pies? Well, we had 80 out of 100, or 0.8. And that's how I got my p hat. This is very similar to how a lot of your problems will work when you're dealing with confidence intervals with p hat if they don't give you the number directly, or hypothesis testing that involves the sample proportion. So keeping that in mind, that's how I like to relate it. You, of course, do not have to, but that's fine. And then this statement just saying that this is typically used as an unbiased estimator of the population proportion, which is a lot of jargon for saying this will get turned into this when we use some formulas and we know we have a normal sample. So with our normal distribution, these are getting pretty small, which is why I will zoom in for us. Now, this is where we start to diverge in that different professors like to use different tables for the normal curve, which means these will work slightly differently for each of you, which is not a bad thing. That's just how your tables will work. I prefer some tables over others, but if you've been using it, you don't know the wiser unless I told you, and we'll be in good shape. So with these curves that we have drawn out, if you were asked a question, what's the probability that z is less than 2.36? Well, where would we start? Well, z, first we need to know whether or not that z is positive or negative. Here we can see it's positive. We know z of 0 is in the middle of a normal curve. We know that 2.36 is going to be somewhere right about here. It's just the estimate. I just like to do a rough drawing. And then probability that z is less than that is looking at area to the left. So basically, whichever way that's pointing, to the left of 2.36. So we can shade in this whole section of the curve. So when you look at your table, some of you, when you look at 2.36, it's going to show you the area from here to here, like this super dark chunk that I'm shading, which is the area from the z down to 0. It'll give you that area. And some of you, it'll give you just the straight up answer, because it's going to add in this 0.5 of the curve for you, which is totally fine. Less work for you. Either way, it should come out to around 0.9909, so over 99% of the area. I don't want to spend too much time on this with you guys because I know we got some more stuff to do. So I'm trying to pick the best ones or the more conceptual ones. So I'm going to let you guys handle most of these at home because you all have different curves and I don't want to confuse anyone speaking about one curve versus another. If you have a specific question about your curve, if you're like, hey, those problems in the packet, I have no idea how to do them, come up here, bring your curve with you, and we'll chat through it together. It'll take 30 seconds. We'll be golden, okay? So this last one here, though, I do want to chat for a second about probability of z being less than 4.98. Well, normal curve, well, most of your tables, where does it end for you guys? Where do z's typically stop, like the highest one you have? 3.5, somewhere in that range, right? So that's a problem for us, isn't it? If we have a z of like 4.98, it's about 5. Our curve stops at 3.5, 3. So where do we put it? Well, we know 4.98 is a very positive z-score, right? So if we know 3 is like here at the end of our curve, let's just say 5 is like here. I'm just rounding now, 4.985, whatever, we're just working with numbers. So they asked, what's the probability that z is less than that? Well, the area to the left of 5, we just need to recognize that's the whole curve. All of this area is below z of 5. So the probability of that should just be equal to about 1. So this is a more conceptual question where, oh, it's not on my curve, what do I do? We have to know how to interpret the curve. Similarly to if we were asked probability of z being greater than 5. If we had something like that, then we'd be working with a curve. Oh, 5's over here. Oh, there's no area there at all. So that probability would be equal to approximately 0, going the opposite direction. So just keep that in mind. These are all good practice, and you can kind of take a look at those when you get a chance. So now, if we're talking about binomial distribution, which I know we did some work on earlier in the course, we have a pretty scary looking formula. Some of you guys probably didn't see it written in this form, which is fine. Sometimes this chunk here is just written as that because it's just a combination. This is actually just what we did before. So you might have seen it written as something along those lines, where this 1 minus p just turned into a q. Because if you remember, q equals 1 minus p. And then this whole thing just got condensed down into the combination phrase. So don't be scared by this formula. It's not meant to, freak anyone out. And if we look at our tables, those binomial tables way back in the day, you have different tables for different n's. So different samples have different tables. You might have an n equals 5 table, 6, 7, 8, 9, 10, 15, 20, 25. Probably doesn't go much higher than that because then we're going to be using the formula. But you have tables for each of those different n's. So if we were to apply that with this example, we have LA Times, very probably trusty news source back in 1992, reported that 80% of airline passengers like to rest or sleep on their flights. Does not really surprise me. So suppose that the actual percentage is exactly 80%, and consider randomly selecting 6 passengers. So we randomly rope 6 people off and we start asking them things about what they like to do on airplanes. So let x be the number among the selected 6 who prefer to rest or sleep is a binomial random variable with blah, 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 blah. So they give us this info. Now, the important thing is that, one, they tell us it's binomial. They do not have to tell us it's binomial, because there are some properties of binomial experiments that we need to know, namely that we have a fixed number of trials, that we have 2 possible outcomes, success or failure, and a couple more beyond that that are in your book and in notes. So here they just tell us, which is great. So we can work with that, but I would also review those guidelines for what constitutes a binomial experiment. So in this case, we're just going to consider a success is a response where the passenger tells us, yeah, I like to rest or sleep on my flight. We'll call that a success for our trial. So they tell us n equals 6, p is 0.8. I don't know if we have tables for these. If you do, great. If not, we're going to math it out and make sure we can do it by hand. So they say calculate p of 4 and interpret, calculate p of 6, and then they kind of interpreted that one for us. So p of 4, the probability that 4 of the 6 passengers that were asked this question like to rest or sleep on their flight. So we can kind of just start rolling with numbers here. If we're working with part A, what's the probability that x equals 4, that 4 of the 6 selected passengers like to rest or sleep on their flight? So if we're plugging numbers into our formula here, we had the grand total of 6 people in this party that they started. We asked 4, 6 minus 4 is 2, factorial. And then they told us p is 0.8 raised to the x, which is 4, same x that's over here. And then q, if p is 0.8, q will be 0.2, or 1 minus 0.8, raised to the 6 minus 4, or square it, basically. And that should do it in terms of math. We're going to run all of those numbers through our calculator. And we'll get around 0.246. And if you happen to have an n equals 6 table, this should match whatever number is there for x equals 4. What I caution you on when using your tables is to be solid on how to read it, meaning some of them are cumulative tables to where they keep adding the prior probabilities as you move down. Some of them do not, where it's just each x has its own raw probability. So I encourage you to either ask me if that's the case, in which case come and show me your table and I'll look at it, or if you know, to really know, and make sure you have an example written out somewhere that you can follow as a guideline to make sure that you're using the table to the best of your ability. When in doubt, formula will work. All your tables are points that are basically generated with this formula. They just put them on a chart so that they're easy to read. So when in doubt, you can go back to this. So this probability here, 0.246, essentially tells us that there's a 0.246 probability that 4 of the 6 selected passengers off this flight prefer to rest or sleep when they fly. So what that actually means to us in the grand scheme of life, I don't know, but for this problem, that's our answer. Now, in part B, they ask us, how about for x equals 6? Well, probability that x equals 6, we keep doing numbers. We have 6 factorial over 6 factorial minus blah, 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 blah. Oh, that's a fun one. So this will be 6 minus 6 factorial. 0 factorial is just 1. That's like a property of that. If you were to plug 0 factorial into your calculator, it'll spit out a 1. So make sure you know that. Don't make this 0, because if this is 0, you'll do 6 factorial times 0, which will give you 0, and then this whole thing becomes kind of nonsensical, which will hurt your grade. So we don't want that to happen. Make sure 0 factorial will just be 1 if you're doing the maximum possible out of the group. So 6 factorial over 6 factorial, that will also come out to 1. So this whole thing basically goes away. And then you're working with 0.8 to the 6th power times q of 0.2 raised to the n minus x, or 6 minus 6 to the 0 power. So this will go to 1 as well. And that will give us a final answer of 0.262, right around there. Now what you're noticing is that all of these numbers, whether we're working with x equals 4, x equals 6, are sub-0, sub-1, I should say. They're all above 0. They all have some probability, right? Probabilities are between 0 and 1. You can have a probability of 0. You can have a probability of 1, 0 being never going to happen, 1 being always going to happen. But for binomial probabilities, what will happen is your probability of the lowest x value plus the next x value and the next and the next and the next, if you even had 100 things in your set, all of them added together should total to 1. Okay, so that's a property we need to be aware of. Each of the possible values in our set, if we were to add up the independent probabilities for x equals 1, 2, 3, 4, 5, 6, they will total up to 1, which allows us to do some kind of easier things when we work with the table. So if you have questions about that, just come find me during the break and we can have a quick chat. And there are also videos online on how to use your binomial table and all that sort of thing. Just make sure that you're using the same style table that you have. And then the rest of them pretty much will invoke some of that rule in part C, probability that x is greater than 4. Now, the main thing with these types of statements is to know what they're asking for. If they want probability that x is greater than or equal to 4, the x's that apply to that, 4, 5, 6. We can't keep going. We can't say 7, 8, 9, 10 all the way to infinity because our sample is capped at 6. They said we sampled 6 people. You cannot have an x equals 7 here. So just know that if they ask what's the probability that x is greater than some number, you can't go higher than the cap on your data set. So however many things they sampled, that's your max x value. So if they had sampled 10 people, we would be doing 4, 5, 6, 7, 8, 9, 10, and we would stop there. So just keep that in your mind as well. So with this, we already did 4. We actually already did 6, so we would really just have to do 5. 5 comes out to, once we do the math, 0.393. So what would happen there is you would just add up the probability for 4 plus the probability for 5 plus the probability for 6, and then you would call it a day. All of those added together, I'll just write it out for you, 0.901, and that just involves adding that 5 in, which we get when we plug 5 into the formula and do our math just as we did before. So if you're scared with that, you'll see the solution manual, you'll be like, oh, that's not that scary. So, and I will post that right after we're done with the session here. So we are at 9:02. Why don't we take a break for a couple of minutes before we get into some confidence intervals? So let's break for about 5-6 minutes, and we'll see you all back here. Okay? Thank you. Yeah, sure.
Right here, how is he got the, like, did I do this right? The 6 minus 4 and everything?
Yeah. Sorry, I was just turning off the mic so I don't blow your ear out. So with this here, this guy, I'll show you on the calculator to make life easy. So if we do 6 minus 4, this is really just 0.2 to the 2nd power, 0.2 squared, that times...
So how do you got those exponents? That's where I was confused.
Oh, from the formula. So what you're missing here are a few values.
Oh, okay.
So in the formula, it's p raised to the x, and then 1 minus p raised to the n minus x.
Okay.
That's why. Yeah,
Okay,
that's
so
all
then
those
when
came from.
Into the calculator, then it just, like, the exponents, then it
Yeah, as long as these are right exponents, it should all just fall through.
And then for right here,
Mm-hmm.
what is it you're doing when you're drawing in your sunglasses?
So with these, you don't have to draw a picture, but I like to draw a picture to where if I have a curve here, oh, where's 2.36? Yeah, it's right about there. And then I will shade in the curve corresponding to whatever area they're looking for. So if they want z less than that, I'm shading to the left of the z I just labeled.
So shouldn't it be, so it'll be like the left side they're talking about?
Yeah, so it'll be the whole left side of the graph plus the area from 2.36 down to z of 0. So it's like it just gives me a guide of how big the chunk is. So I'll give you an example here. If we were looking at this and we had, like, that's my 2.36, if I know I have to shade all of this, my answer has to be greater than 0.5, right? Because this half the graph, just this part alone is 0.5. So I might be able to look at answer choices and eliminate everything that is less than 0.5.
So let's say like z is greater or less than 2.36. So I just know from here down.
Yeah, yeah. It's just like a quick picture to kind of be a guide. Is that it? Yeah.
Thank you.
Thanks, man. Hey.
Okay, so for the last part, I kind of missed it. This is what we get once we solve this with 5.
Yeah, you'll just plug 5 in for x and same process.
And this will be the answer.
Yup.
Okay.
And then that last part is just adding each of those together to get greater than or equal to 4.
Okay, thank you. And then for this, you said something about the graph. Which graph would we use for binomials? Do we
Graph.
use that?
This will be your table for binomial.
Okay.
That is true. And what I was saying is that you have different tables for different ends. So for this problem, you have an n equals 6 table, you'd be using this table.
And then what would I need that for to get the answer? Like,
For this problem, they told us p was 0.8, so you'd be over here at p of 0.8. And if we want to know, I'm trying to see if your table is cumulative or not. They don't even give you 6 because it's going to be 6 minus this. Yeah, because your table is cumulative. I would have to look at it for a few more minutes, but this...
So is it just best to use the formula? Like, I don't need to use this?
You will want to use this if you can, because this will be faster.
Okay.
That's the main benefit of this, is it's much faster once you know how to use it. They're all just a little bit different, so I'd have to sit here and figure it out. Usually what you'd do is if you want just 4 for this, you'd be looking at 4, that 0.345 number, minus 0.099. I'll show you what I mean. So we have 0.345, the value for 4. Minus 0.099 will give me 246. Oh, wow, look at that. 4 was 0.246.
Okay.
So the way this works is you have to like yank out the one that came before it, which I don't have time to explain right now. But yeah, you could probably find a tutorial online that'll teach you how to do it.
Okay.
But yeah.
Thank you.
Hi.
You answered
Good
my
morning.
question with her.
Oh, good. Awesome. 2 for 1.
I was trying to figure out how you did that one, how you got the answer to it.
For which one?
This one.
This one?
And how do you do it?
So yeah, we're going to need your table. So you want normal curve. Cool. You want if I draw on your table?
Yeah.
Or no? Okay. So pretty picture time. So if we're working with, let's say, 2.36. You don't have to draw a picture, but I like to. So if we have 2.36, it'll be on the right side, approximately there. They said, what's probability that z is less than 2.36? Well, that's like everything this way, right?
Right.
I know that from 0 all the way that way, this whole chunk of the graph is half, right?
Right.
Half the graph's on the left side. Now from 2.36, we have a value of 0.4909. That is the area from 236 to 0. So how do I get the whole thing? Well, we just add these, and we get 0.9909.
Oh, okay. And what were you saying about the table with her?
For binomial?
Yeah.
Depends on your binomial table. Let's see. So these guys, yeah, yours are also cumulative. So what happens is, if I want to know what's the probability that x equals 4, like what we did in the binomial problem, if we take this number and we subtract the number before it, then we will get the number that is just x equals 4. Because
So the
as
number
it,
before it, like 0.99.
yeah, so
Okay.
as this sits, if you were to write down 0.345, it would be incorrect for x
Right.
equals 4. This is actually representing probability of x being less than or equal to 4.
Okay.
So this number includes 0, 1, 2, 3, and 4 all added together.
Okay.
So it's kind of confusing,
Yeah.
but yeah, once you practice with it, you'll be good.
Okay.
So I kind of didn't understand what you did right here, like you circled over here and whatnot. How'd you get 95%? Basically?
So C is referring to part A, right? So this had 3,500, 5,500. This was the z-score of -2 and +2. By empirical rule, if I want to know what's the area between -2 and +2, it's just approximately 95%. There's nothing else you have to know there.
So how did you get 99.7% here?
So this one is referring to 3 standard deviations from the mean. This is just the same thing as before. You just have to
Okay.
know it's
Okay.
about 99.7%.
Alright.
Yeah, I wasn't doing anything like fancy. It's just a
Okay.
property. Yeah. Yeah. How's it going, guys?
Question. I kind of like what she was asking you.
Yeah.
I'm just confused as to how to use the, like, why this, when I go from, like, I'm with 6 and then we were looking at 4 at 0.8,
Mm-hmm.
wouldn't that just be the answer?
You would hope, right?
I would
So
hope.
what this number actually includes is that's 0, 1, 2, 3, and 4 all added together. It's a cumulative table. So if you're looking at 4, that's actually 4 plus 3 plus 2 plus 1 plus 0. They're all put
Okay.
together. It's stupid, I think, but yeah, so if you want just 4, you have to do 4 minus the number for 3, and then you'll be left with just 4, if that makes any sense.
Okay, but then if you want,
If you wanted x less than or equal to 4, this is very useful, because you just look at 4 and that includes them all.
okay.
So you just write that number down.
So if we're just looking for 4, then we would have to subtract the rest of the number?
You'd have to subtract 0.345 minus 0.099. Because the 3 will include 3, 2, 1, and 0. So you're doing
Okay.
4, 3, 2, 1, 0 minus 3, 2, 1, 0, which will leave you with just
okay,
4.
okay.
But
Yeah,
then for the
it's
one
weird.
Where we have to include them now, we can't do that because it goes up to 6 and we don't have 6 on here.
6, so on this one, if it goes to 5, and you're looking here at 0.738, the 6 will be 1 minus that. Will be whatever's left. Because all of them together have to equal 1.
Together.
Yeah.
Okay. Okay, thank
Uh-huh.
you.
Yeah, no problem. You have a question?
Yeah.
All right, cool.
So you have like A and B, right? So Z is less than 2.36. You would just like look at that on the chart, but how would you do less than or equal to 2.36? What's the difference?
Oh, you're saying between A and B here?
Yeah.
So this has to do with a property of the normal curve. I'm going to actually talk about this when we come back from break. That way we all know. This here, the only difference between these, like you said, is that equal sign, right? So the property of the normal distribution or any continuous probability distribution is the probability of being at any point is 0. So the only difference between these is Z actually equaling 2.36, right?
Okay.
So the difference between these is basically what's the probability Z equals 2.36. For this, we always say 0 because that is a point on the curve. There's no area at that point.
Okay.
So we would say that's 0, so there is no difference between these.
So whatever number's here is the same number there.
Same exact thing, yeah.
Interesting.
It doesn't actually matter. That's a very conceptual question. We might chat about that for a minute,
Alright,
but yeah,
thank you.
good question. Yeah,
Sorry, really quick again.
sure.
Right here, I understand the 0.8 came from the probability or whatever,
Mm-hmm.
but how did you get the 0.6?
0.6. Did I write 0.6 somewhere?
Oh, did I read it wrong? Oh, my.
I hope I didn't write 0.6. Oh yeah, that's totally my bad. Whoops.
Also, what is it, 0.8?
Yeah, it's the same number. It carries through.
Be 0.8.
That's for this problem, yes, because it's always referring to the p. P, they told us, p equals 0.8. Yeah, p equals 0.8. So that's my bad, but yeah, I probably stupid handwriting.
Okay, and then
Yeah.
for this part, when we do the 5, it's as well as 0.8, correct?
Yeah, the p will be the same for all the x values. Doesn't matter what x we're working with. Yeah, yeah. Not for every problem, but for this problem, yeah. You got it. Uh-huh. All right, guys, I'm just going to let you guys do some reading. I'm going to be right back. Just grab some water. You catching bugs? Kids are funny. Alrighty guys, we good? Everybody nice and cozy? Good break? Everybody check your Facebook, Instagram. Yeah, awesome. So did anyone not get one of these yet? I just want to make sure everyone gets one. They're the eval forms, so I'll come pass around a few. These are for later. You don't have to fill them out right now. I just need them by the end of the session. Thank you. Wow. Well, so many wires. No, it's not your fault. All right, cool. Thank you again for being here, guys. I know it's early. If you didn't get one, I'm just going to leave a few at this table. Feel free to grab them later. Not important yet. Any other last minute things before we move on to the next segment? All right, cool. Guys, final stretch. We are in the zone. It's what, 9:15, and we have until 10, so let's crank on through this. So we're talking about confidence intervals. Now, confidence intervals, we are confident. Isn't that like a Demi Lovato song or something like that? So we can do these with a few different things. We have different population characteristics we could be working with. You might be working with a sample mean. You remember from before, sample mean was x bar. Or we could be working with a sample proportion such as p hat in this case. So I know you guys have seen lots of different formulas doing with all these, and you've probably at this point probably started to confuse them with test statistic equations and formulas for hypothesis testing. But for this section, we're just dealing with confidence intervals. So one common theme amongst your confidence interval formulas, they're going to have this guy. That plus or minus, that's what enables us to create an interval and use interval notation at the end of the problem. So if you're using a formula to make a confidence interval, please make sure it has a plus or minus in it, because otherwise you are probably not using a formula for a confidence interval. So just a fun fact there. Now, if we remember from before, just like with my sample of people at Walmart that I asked about apple pies, we have p hat equals x minus n. X could be whatever. It could be the number of people who said, yeah, I like apple pie, it's my favorite pie. Or if the problem said, what is x, the number of people that dislike apple pie, in that case, out of my 100 people, if 80 of them said, yeah, I love apple pie, 20 of them would say, no, I didn't like apple pie. So it varies based on what the question is asking. So be careful. They could say, we sampled these people, they said this. What is the opposite of that, or kind of like that? What's the word in probability that we use for the not statement? Remember that? No? All right, I'll let you think about it. Come back to it. So we've got this formula. We're going to talk about buying pets gifts on Valentine's Day, because it's not like we would buy people gifts, we buy pets gifts. So they give us a bunch of background here, which you could be given on an exam. I don't know if it would be likely. It might be not that crazy. But you could be given something, and part of the skill of a Stats 2023 student is being able to pick through the nonsense and find the numbers that matter. So if I kind of ignore all this stuff, knowing they're going to ask me about Valentine's Day gifts because I've read this problem before, they're going to say the proportion that responded they planned to purchase a gift for their pet was 0.173. So the proportion who responded, p hat sample proportion, is 0.173. I'm starting there. Suppose that the sample size for the survey was n equals 200. Might as well write that down. Construct and interpret a 95% confidence interval for the proportion of all adult Americans who plan to purchase a Valentine's Day gift for their pet. So that's the interesting thing. What we do here is we take this sample of 200 people and we try to make an inference about all Americans that like to buy Valentine's Day gifts for their pets. So that's kind of a big leap, but it's what we do with inferential statistics. So 95% confidence interval, that's going to trigger a couple of things. One, we know we're working on the large sample, n equals 200. If we remember from before in the class, we know n greater than or equal to 30 by central limit theorem typically will be a normal sample or fit by a normal distribution. N of 200, therefore, will be probably very normal, in which case we can use the z distribution by central limit theorem. So that is partly why our large sample formula includes this guy, z of alpha over 2. Now, Justin, I know what z is, but what the heck is alpha over 2? Well, if they say we have a 95% confidence interval, alpha is just left over from the 100% of the curve. So if we had 100% in our curve minus the 95% interval that we're grabbing, we have 5% left over. Alpha is 0.05. These are usually much more obvious with the hypothesis test because they usually tell you what alpha to test at. But just know that's how we got it. It's just based on our percent confidence here. So this alpha will get split on our curve. Now I'm going to kind of draw you a little picture in case you haven't seen this before, to where if I want to know, what's my z? We have 95% that we capture here and here. We know our alpha, 0.05. Well, half of that has to go here, half of that has to go here. So alpha over 2, 0.25 on both sides. So these tails both have 0.025 in them for the area. Now there's some z here, there's some z here. One's positive, one's negative. We call them z of alpha over 2 because they are generating that half alpha area in each tail of the curve. So that's just a bit of a semantics game, but for our purposes, we just need to know what z is here. Most of you already have them written out, so I'm not going to spend too much time going through curves. We know z for a 95% confidence interval should be 1.96. So that's our critical value for z that we will use in our formula. So now we pretty much have everything we need. They wanted us to make this confidence interval. I don't think we have any missing links here. So if we start with p hat of 0.173 plus or minus the rest of the stuff in the formula, we had z of alpha over 2 or 1.96, our number we replace, and then our 0.173 again times 1 minus 0.173 over n of 200. The most important part, take the square root. See, it's so important you break your pencil in half. That's very important. That radical enables us to estimate the standard deviation of this sample rather than the variance. That's essentially what that radical does for us. If you forget that, you will get an interval, but it will likely be an answer there, and it will likely be the wrong answer there, because one of the most frequent mistakes is to forget to take the square root of all this stuff. So please don't forget to take the square root. If I had a formula sheet, what I would do is probably have this formula written down, and I would highlight that radical. I would be like, do not forget this, because if I forget this, I will be wrong and it will be sad. So please don't forget that radical. So the way this works is we do all that math under here, under the radical. So you do this times 1 minus this, and then over 200. Take the square root of that whole thing, multiply by 1.96, and you'll get some number. So that number, 0.0524 is what that comes out to. On the left, we just had our p hat, 0.173 left alone. So this is pretty good. Now, you very well could have answer choices that are written in this form. I have seen that happen, where you just have the characteristic plus or minus. This would be like the standard error of the mean on the right side here. So, or the sampling error, sometimes they're referred to as. You could have answer choices in this form. Most of the time, though, final answers are written in interval notation. So we'll do 0.173 minus the right side to get 0.121, and then 0.173 plus the right side to get 0.225. Put it in some parentheses and you can call it a day, kinda. Because we now have our interval, which is great. But what does it mean? What does this interval have to do with anything? That's more so what questions we'll like to ask. You might have to give an answer choice for a very brief selection that's essentially explaining what this interval is referring to. So when we interpret this, we usually start with our percent confidence. We say we are 95% confident that and then we start talking about stuff, that the proportion of adult Americans who plan to purchase a Valentine's Day gift for their pet is between 0.121 and 0.225. And you don't usually have to say any more than that. If your professor requires it, then that's something I would need to know. But that's pretty much all we would need. Just we are this percent confident that the proportion, or if you're working with the mean value of blah, 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 whatever the question was talking about, is between this and this. And that's typically all you're working with. So usually those don't need to be overcomplicated, but they are very easy to mess up. So take a look at the examples I have in the packet, and I think you guys will be in great shape from there. Now, I have another problem there that's very similar, the next one. You guys will be fine with that one on the review guide. Why don't we shift over to hypothesis testing, which is on page 9. Where we will first have a quick chat about type 1 and type 2 error. So test of hypotheses. Oh, that glare is so bad. I'm sorry, guys. I'm gonna like hold it with my fingers so it doesn't do it. So we have type 1 and type 2 error. Type 1 error is what happens when we reject the null hypothesis. What's the null hypothesis? Null hypothesis is referring to HO, right? When in fact it is true. So we're rejecting HO when in fact it's true, meaning we rejected HO, but we shouldn't have rejected HO. That's a type 1 error. Type 2 error is when we basically didn't reject HO, but we should have rejected HO. It's like the opposite kind of mistake, okay? So that's our type 1 and type 2 error. Now symbols for these guys, type 1 error denoted by alpha, type 2 error denoted by beta. Alpha, usually they will give you some alpha or significance level. In the problem. It's good to know synonyms for things. Alpha is your significance level, but it's also your probability of a type 1 error. Those are all things to know. Those are usually given to you in the problem. Type 2 error beta, typically we don't calculate that in stats 1 because it's more involved. All we really need to know is that as alpha increases, beta decreases. As beta decreases, alpha increases. They are inversely related, okay? So that's the main important thing there, is that we have a distinction between type 1 and type 2 error and being able to apply them in the context of a problem. Now, if you, in real life, are trying to run a hypothesis test, you might really not want to make a type 1 error. Like, that would be really bad if you were to do this test and you made a type 1 error. So if you really don't want to make a type 1 error, we're going to try to reduce the probability of that happening, reduce the probability of type 1 error. So we will reduce alpha. We're going to use the smallest alpha we can. Alpha is typically going to range between 0.01 and 0.1. That's usually like the given range of where we'll see these problems occur. So let's say we try to use an alpha of 0.01. What we sacrifice for that is a higher probability of type 2 error. But if we don't care about making a type 2 error, then who cares? Then we're fine. But if you are a company and you're running this test and you really don't want to make a type 2 error, then you will accept a higher alpha in order to reduce your probability of a type 2 error or beta occurring. Okay? So just know that this in real life will vary depending on your perspective. If you're running this from the perspective of consumer versus the company that's, say, producing a product that has a warranty or something associated with it, your willingness to accept a certain type of error might be very different from that regard, okay? And there are tons of examples of this online too, so I want to beat it to death, but just definitely know the relationship and which symbols denote which and how they affect each other. So now with this guy, all I have written here is test statistics for a hypothesis test with Z for a given proportion. This is, of course, using a large sample because we're not using any of that like adjusted sample stuff. Different professors in the past have used different sort of adjustments. You might have seen like a P with like a squiggly line over it, or a PC back when we were using some paired samples and things like that. So it varies a little bit from professor to professor and the book. So I don't want to do anything that's too out there because I know you guys have some specific stuff for your classes. But this is pretty standard. This is basically the go-to for a large sample test utilizing a proportion. So that being said, let's read this thing. So we have a bunch of distracted drivers. Some report looked at a sample of 283 teens aged 16 to 17, are young drivers where insurance is crazy expensive. There were 74 indicated they've sent a text while driving, and this was in 2009. Can you imagine what that number is now? So for this exercise, assume sample is a random sample. That's nice. That falls in line with some of the assumptions we make when we do these tests of hypotheses. You have a random sample. It's a representative sample of the population being studied, those sorts of things. I'm not saying you need to know those, but those are great to have written down, just key items. Oh, we need to meet this and this and this requirement in order to run this test. Not that you'd ever be asked, is it even possible to do this based on our knowledge of the problem? I haven't seen a question like that, but it's fair game, so might as well have it written down. So do these data provide convincing evidence that more than a quarter of Americans in this age range have sent a text while driving? Test the appropriate hypotheses using a significance level of 0.01. Now, oh man, what's significance level? Well, if we remember back from 2 minutes ago, we know significance level is synonymous with alpha. So we'll just put an alpha here. So alpha of 1% or 0.01. Those are the same thing in my eyes. So now how do we know we're working with a proportion? Well, they ask us to see if there's convincing evidence that more than a quarter, well, they didn't give us a raw p hat, they didn't give us a raw p to work with regard to HO and HA, so we're going to have to do some digging with words. More than a quarter, that should trigger us to think greater than 1/4, right? That's more than a quarter. So that is what we're testing for. That's going to be involved in HO and HA. Our p hat, that came from the sample. If we remember by definition, p hat sample proportion, they told us they sampled 283 in this representative sample of teens, and 74 indicated they sent a text. So if I want proportion, a p hat, proportion of those in the sample that sent a text, we're just going to say, oh, that's 74 out of the 283. Now, if you want to, be awesome and convert that to a decimal, that's fine. You can do it. But if it comes out to some irrational type situation where it just keeps going on and on your calculator, if you aren't using that whole length and storing it as you carry down in the calculation, you're going to be losing decimals as you go, and that can hurt you in the end. Because sometimes these small numbers, if you're off by a little bit, it can be off by a lot by the end of the day. So my recommendation is just leave it as a fraction. Perk of using a graphing calculator, you can store it as x. You can do whatever you want, just you're not sacrificing any of the accuracy. So we have p hat. Now, my first step is let's get HO and HA going. Now, we didn't even chat about this. What's HO and HA? Well, HO, we said before when we were talking about type 1 and type 2 error, HO is our null hypothesis. Our null hypothesis, we typically already assume to be true. It's kind of like the status quo. It's like the unchanging, we already kind of think this is what it is, but maybe it's not, I don't know. So HA is kind of out to get HO in that we're trying to see if there's evidence to the contrary or something different. So HO, we're initially assuming that the proportion for the whole population of team drivers, that's why we use p here, not p hat. We're not assuming that the proportion of the sample is this. We're assuming this is true for all team drivers. So for HO and HA, typically you'll only either see a p there or you will see a mu there. You will not see an x bar. You will not see a p hat, those sample characteristics. So we're going to assume that the proportion is 1/4. And they asked us, is there evidence that it's greater than 1/4? So I'm just going to use that for HA, the research hypothesis. Cool. So we've got HO and HA. Next step I like to do, let's just do the test statistic. We'll just run some numbers. So in this case, we're using a z because we have a pretty large sample of 283 people. We can assume that's normal by central limit theorem. So we have z equaling p hat. And this p naught, your formula might not have p naught in it. P naught is just the hypothesized proportion, or our 1/4 that we used above. And then this will be over the square root. Again, this square root, this square root, this square root. Please highlight this. Do not forget to take the square root. And then we'll have p naught, 1 minus p naught over n. And so when we run some numbers into here, we have our p hat 74 over 283. I'll group that together, minus the 1/4 from the start of the problem. And then we have this same 1/4 times 1 minus 1/4, which will be 3/4 over n, which was 283. Take the square root of the whole thing, and then we do some math, and that should come out to a z of 0.45. So that's great. So we're going to leave that alone for a little bit. This z does not always have to be a number that you might consider reasonable. I have seen questions where this z comes out to like 8.5, negative 12.2. That's okay sometimes if it's the right answer. If you get an extreme value like that, if I have time and I'm not like flying through the test because we're running out of time, I would recalculate it just to make sure something didn't go crazy wrong in the problem. But if you are consistent and you checked your numbers, it is possible to get a crazy z, and then that still applies through the rest of the problem. So don't be totally discouraged if your number seems a little bit off from these. Now, what do we do from there? Well, we have some options. We can do a rejection region. Or if you guys remember from probably more recently in the course, I think we did some work with p-values. So we can do both. We might actually look at both if we get a chance with this one, but we might just stick with the rejection region. So if we're working with a rejection region, we have 3 main types that we work with. We have a one-tailed upper-tailed test, one-tailed lower-tailed test, and we have a two-tailed test. Now, that will essentially be determined by whatever symbol is here. So this guy, greater than 1/4, this guy's pointing to the right. We're doing an upper-tailed test for our rejection region. If this guy was this symbol, that would be lower-tailed. This symbol, the differs from or does not equal, that will be two-tailed. Okay, but in this case, we're dealing with an upper tailed test. So, well, Justin, what the heck does that mean? Upper tailed test, basically looks like a brick, but it'll work for us. So, z of 0, assume it's a normal curve. Upper tailed test means I'm going to have some tail on the right, on the upper side of the graph. The area in this tail is equal to alpha. All of my alpha is in this area of the graph. So in our alpha, they told us was 0.01. So now we need to find this z of alpha of 0.01. That way we can decide where our rejection region is based on the z. So when we look at our table, I don't want to spend time on this too because I know we have different tables that work differently. We need to know that it's 2.33 will be our critical value of z here. So basically, we'll reject HO if our test statistic is in this shaded region, this rejection region. So I'm going to just write this in words. If test statistic is greater than 2.33, reject HO. Now, if we remember from before, our test statistic was 0.45. So then we ask ourselves, is 0.45 greater than 2.33? No, 0.45 is like over here. So we are not in the rejection region. So we will say, do not reject HO. That's our decision. Now, when we talk about p-values, we can also recognize for this scenario, we would be doing probability of z greater than 0.45 will be pretty big. It'll be like 0.4-ish, which will be much larger than our alpha, which will indicate to me that we will not reject HO. So that will agree based on my knowledge of p-values. If you're not quite there with the p-values, though, this works just fine. We just need to know that our test statistic is not in the shaded region, because the shaded region is our rejection region. So then, same thing with confidence intervals. We have to know how to interpret it. What does it mean to not reject HO in this case? Well, in our conclusion here, usually we'll start by saying, do not reject HO. That's a great place to start. You want to give an answer. Now, I know we're not giving a written test, but if you were given a multiple choice selection to work with and you had to pick one, 2 of the answers will probably say reject HO. 2 of them will probably say don't reject HO. And right from there, hopefully you can narrow it down to 2 answers and figure out which one's right. So we will say do not reject HO. At the alpha equals 0.01 significance level, there is insufficient evidence to indicate that the proportion of Americans ages 16 to 17 who have sent a text message while driving exceeds 0.25. Now, Justin, where did 0.25 come from? That came from our HA. We were testing to see, does the proportion for these teens sending a text while driving exceed 1/4 or 0.25? Those are the same statement. So all we're doing is stating whether or not we're rejecting HO. We're stating what alpha we used, because that can kind of sway our decision if our test statistic z is anywhere close to our z critical value. If we're rejecting HO, we're saying that we have sufficient evidence to do so. If we're not rejecting HO, it's because we have insufficient evidence to reject it in the first place. So those answers will always go together, that wording. And then the rest of it, you're just basically filling in the rest of the problem, whatever they were asking for. Exceeds 1/4, was less than 1/2, was differ from 0.33. Whatever they asked you in the problem, you're just going to fill that in at the bottom, which I'm sure you've seen in the homework and all your problems that you do in class. So any questions on that or the wording of the conclusion? Yours might not be identical, but it'll be close. Yeah? Okay, so gotcha. So the question is, when do we say we have sufficient evidence, say we have insufficient evidence? How do we know what goes with what? So if I were to write this out real quick for you guys, if we are rejecting HO, we have sufficient evidence. We need to have the evidence in order to make the claim that, oh, reject HO. Now, if we are saying do not reject HO, we're going to say that there's insufficient evidence to indicate that whatever they were trying to prove with HA. Okay? So if we're rejecting HO, we have sufficient evidence to indicate that whatever they said with HA. Okay, which is exactly what didn't happen in this case. We said there's insufficient evidence to indicate that the proportion for teens that are driving while texting or whatever it is greater than 0.25 or 1/4. If we had rejected, we would be saying reject HO at the alpha equals 0.01 significance level. There is sufficient evidence to indicate that the proportion of teens who text while driving is greater than 1/4. So that's the varying degree there. If we're rejecting, we have sufficient evidence. If we are not rejecting, it's because we have insufficient evidence to indicate whatever the heck HA was talking about. Does that kind of make sense? Answer your question? Okay. Anything else on that? Cool. Let's see what's next. Yeah, let's do a two-tailed example. That'll be good. So on page 10, we have an example that involves two tails, which I kind of gave away to you guys, but you would have figured it out anyway because you're smart. So we're talking about legalized gambling appearing on state ballots. So some candidate has decided to support legalization of casino gambling if he's convinced that a proportion differs from 2/3 of Americans approving casino gambling. So as you can see, I definitely changed this question, which is okay. It said something else, but we just changed it to differing. That way we get an example with two tails. And that's okay. So we're going to have an HA. We're going to have an HL. I'm not even reading the rest of the problem yet. I'm going to at least write that out. Now, they tell us, suppose that 1,035 of the people in a random sample of 1,523 American adults approved of casino gambling. Well, to me, they sampled those people. That's a sample proportion. P hat. So I'll start by writing that down. Now, if we're working with P hat, I know I'm dealing with P for these guys. This guy will be equal to, oh wow, I wrote this backwards. Good catch. Thanks, guys. So HO and HA. So P will equal something for this guy. This guy, they said they want to know if it differs from 2/3. I already know. We're trying to see. Does it differ from 2/3? That's the question. That number will be consistent there as well. So we've got that. Great starting point. Now, they told us to use an alpha of 0.10. Awesome. So we have alpha. What do we do from here? Well, we have HO, we have HA, we have P hat. They indirectly gave us n, right? Because we know P hat is equivalent to x over n, so this is our n, 1523. Big sample or small sample? Well, 1,500 and something is definitely greater than 30, so I think we are safe to assume that's normal. By our central limit theorem, that is a very big sample. So we can go ahead and basically use the same formula that we just used. So we're going to have our test statistic. That'll be a z, just like before, big sample. So we have z, which is going to not equal twice, but just equal 1035 over 1523 minus our 2/3 all over 2/3 times 1/3 over our n of 1523, and don't forget the square root. Where did 1/3 come from, Justin? 1 minus 2/3 is 1/3, and that came from our formula, which somewhere right here, boop, P naught, 1 minus P naught. So the value that they gave us in the hypothesis minus 1 minus that will be, it's like our Q. If you were to think of Q naught, 1 minus P, same thing going on here. So we wrote that down. We do some math. We're awesome at math. We crunched some numbers. We got 1.10. Awesome. So we have some number. Great. Now, what can we do? Well, just like before, we can use the rejection region, or we can do a p-value. Let's just stick with the rejection region, and maybe we'll even try to do the p-value, but I don't have my tables on me, so we'll see what happens. So we have 1.1. Good to know. Now, our test, just like before, we are basing it off of whatever symbol's going on here. So if we want to know, does it differ from 2/3? Differ from, well, that to me is triggering a two-tailed test. So we're going to have two tails. Shaded tail here, shaded tail here. There will be a z here that's negative. There will be a z here that's positive. The area in each of these tails will need to be half of alpha, due to the fact that this is a normal curve, and a property of the normal curve is being symmetrical. So we have this symmetrical normal curve going on, at which point we will go ahead and write our numbers in. If we had an alpha of 0.10, each of these will have an area of 0.05 or 5%. this should look kind of just like a 90% confidence interval, right? It should look pretty close. And we'll get our z critical values, excuse me, which should come out to 1.645, which will involve a little bit of interpolation on our z table, which we can look at later. So we have 1.645, that's our critical value. So if the test statistic z we got is greater than 1.645, we will be in that shaded region, that rejection region. Is that the case? No, because 1.10, let's say it's there. That's just a guess. So if 1.10 is here, not in the shaded region, so do not reject HO. Excuse my horrible handwriting. So do not reject HO. And then same thing like before. At the alpha equals 0.10 significance level, there's insufficient evidence to indicate that the proportion of American adults who approve of casino gambling differs from 2/3. And that will be fine. End of the day, you got your conclusion. Don't worry about that if you don't catch my words. That is all written out on the packet that I will upload in a couple minutes, so you guys can see how I write the conclusions. No big deal. So the rest of what's in this packet will involve the use of p-values, how to generate p-values. You'll see some examples in there. I know we're at the around 15-minute mark or so left, so I can keep pushing or I can take some time to answer questions from you guys. It's totally up to you. Would you guys rather me take some questions or would you rather me push and do a p-value example? I see some charge on, so we're going to charge on. P-value example it is. So let's flip to page 11. That'll be good. Thanks for sticking with me, guys. I know it's early morning, lots of stuff. We're pushing. So up top here, we have some explanations of how the heck you're going to generate a p-value. Well, you can kind of look at these just like the symbols from before. If you had a one-tailed test, meaning an HA, you had that symbol, that symbol, that symbol. These are the corresponding things that go with that. So these are how we're going to generate those p-values. Now, if we look at this example from earlier, this is pretty much identical to whatever happened when we just did this. That 0.45 that we got in our test statistic, and I remember we said don't reject HO, and I was like, we can do the p-value later. Well, later has arrived, so p-value. What we did before, we had a one-tailed, upper-tailed test, and that's based off of this symbol here. So one-tailed, upper-tailed, we're basically going to follow this one right here. One-tailed, upper-tailed, p-value is equal to p, probability, of z or t, whatever we're working with, being greater than our test statistic value. Now, I'm just going to transplant that on down here. Probability of z being greater than test statistic. That's all I really care about because we're working with z. Now, I'm just going to fill in my test statistic, and we're going to go from there. So we have probability of z being greater than 0.45. Now, this question, this that we're asking ourselves now, looks just like those problems, those like 8 of them that we had drawn out for the normal curve that I said, we're going to be good with these, and we're going to be solid on our normal curve. So if we were to draw a quick little picture, 0.45, probability z is greater than that. That's going to be this area here. I know it's less than 0.5. I don't have my curve in front of me, so I don't know the exact value. But I know, because I have things pre-written, that this area will come out to 0.3264. And this is something I recommend trying with your normal curve. I don't want to do it because it'll confuse people using different curves. So if we have 0.3264, that is our p-value, okay? Now, Justin, how do we make the conclusion based off of that? That's just a number. How do I know whether or not to reject? Well, the way this is going to work is, bam, if p-value is less than or equal to alpha, we're going to reject HO. If it's not falling in that category, meaning if it's greater than your alpha, then we will not reject HO. So in this case, this p-value I would consider to be pretty big, 0.3264. That is definitely greater than our alpha of 0.01. So we will say, do not reject HO. Now, this should always be consistent with what we did with our rejection region. They should not disagree with each other at the same alpha. If you said don't reject HO using a rejection region, you should also say don't reject HO using a p-value. The only way that could ever change is if you change the alpha between whatever you did. Okay? You have a question? Yes. So that's a good question. What happens if it's two-tailed? If it's two-tailed, we're following this guy. We're going to have 2 times the probability that z is greater than the absolute value of your test statistic. Now, why do we need absolute value? If your test statistic came out to a negative number, a negative z, you just make it positive, and it simplifies it when you go to do the math to multiply and get both tails together. So that's all I'm going to say on that. I believe I'm going to have some examples in here that use that, so just take a look, and you'll see that p-value of 2 tails example, and you'll be good with that too. That answer your question? Okay, awesome. So here we said don't reject HO because our p-value is greater than alpha. If our p-value had come out to 0 or 0.01 or 0.001, we would be rejecting HO because our p-value would be less than alpha. So some people really like p-values, some people really hate p-values. Whatever works for you, that's what I like to say, is just do what you're comfortable with. But you could be given a question that asks, using the p-value approach, what is your answer to this problem? Now, you might be thinking, I gotcha. I can do the rejection region. I don't need to do the p-value. I can work around. But the answer choices are going to have a p-value in them. 2 of them might have 1 p-value. 2 of them might have another p-value. And then 1 for each of them is going to say reject or don't reject. So you might be able to figure out the reject or don't reject based on a rejection region, if that's what you're comfortable with. But you're going to need to know how to generate a p-value. So not saying you will be tested on it. I'm saying if I were a professor, I would be testing you on it. So know how to generate a p-value, and that just comes from these and a little bit of practice. And I'm sure that most of you had some big-time homework problems that involve generating p-values. So if you're stuck on any of this, why don't we take the next couple minutes to answer those questions now that we have about 10 minutes left. I have some surveys along the length of the tables. Don't freak out if there are a bunch of problems in the packet we didn't get to. They all have hand-drawn solutions to every part of them. That will be posted in the next 15 minutes or so. Okay? So if you guys have final questions, feel free to come up and ask. But for our purposes this semester, thank you so much for sticking with me. Thank you for coming. Hope you gained something from today. And best of luck on all of your finals. Thanks, guys. Woo! I'm going to unmic.